And in that limit, what are the scattering cross section? What are the perturbative corrections? What kind of, corrections? How do they look like? And then, these are what we call as large logarithms, the threshold corrections. Then what is the idea of this exponentiation that people talk about, pseudo
Sir,
summation?
excuse me,
Yes,
sir. Sir, can you little bit increase your voice in the sense like
little bit.
mic sound?
Okay, 1 second.
Right corner, sir. In the right corner, there must be a.
You can see audio settings. Okay.
You go to this Friday where date is written, sir.
Yeah, is that okay now? Can you?
Perfect, sir.
Perfect. All right. Okay. So then I will go to the, what is the idea of exponentiation? Famously, that is called as the pseudo-curve exponentiation or the pseudo-curve resummation. Then that is based on, the concept of the factorization theorem. And then what is this Mellin inversion and some phenomenological applications of this sense. So this is a broad, plan of my presentation for the next today's lecture and tomorrow's lecture. So let me go into the basics of these things. So what are the basic ideas? So in QCD, we have the, the strong coupling constant, that is, suppose we want to use the quantum field theory and we want to make the perturbation theory as a basic tool, basic ingredient for doing the, any calculation for the scattering cross sections. So in that sense, we heavily rely on the concept of the perturbation theory. And in order to do the perturbation theory, we need what we call this thing, some expansion parameter. So typically the expansion parameter can be taken as a coupling constant, provided it is a very small number. So that is what, the alpha s, which is defined as, gs squared by 4 pi, can be taken as a, expansion parameter for the expansion of the perturbation series. So just let us, without going into the head-on level or any QCD scattering cross section, if you have some quantity, any sigma of z, how do you expand it in terms of the perturbation series? So we can call as the first term what we call as the leading term. And in terms of this expansion parameter, we can write the, first order correction and second order corrections, third order corrections, and so on. So this is a, typically what we call in terms of our scattering cross section, leading order, next to leading order, next to leading order, and so on. But we'll come back to the head-on level cross section. But there's any quantity that you want to compute. Say, for example, using the quantum field theory, I want to compute some quantity as a sigma of z. And if I don't know the complete answer for this thing, so I rely on the quantum, perturbation theory. So for that, I need to have some sort of expansion parameter. In this particular case, strong coupling constant I have taken. Had it been the electroweak theory, so we can take the electroweak coupling as the expansion parameter. If it is a QED, we can take the fine structure constant as the expansion parameter. So the idea is that if each of the terms are finite, okay, suppose if there are no singularities, that's what we can, later it is understood now in the quantum field theory, order by order. If there are any singularities, all the singularities will cancel, and whatever is left over is a finite quantity, which is a perturbatively calculable, and that's what, it gives some contribution to the basic leading order contribution. So under that assumption, so if each of the terms, are actually finite, so then in the limit of small alpha s, only in the limit of small alpha s, though it is going like, perturbation series is going like alpha s power n, where n goes to infinity. So, but because, we are assuming the expansion parameter to be very small, so we can, rely on the concept of what we call as the asymptotic expansion. So in that sense, asymptotic expansion we can consider as a good approximation, for predicting whatever with the, your observable or whatever the quantity that you want to compute. So technically speaking, or, more, simplified manner, if you want to say, in other words, the higher and higher terms in alpha s, that is alpha s power n, where n goes to infinity limit, okay, those terms can be ignored. In another words, so we don't need the full, all ordered result as such. If we assume that thing, each of the terms, like a sigma 1, sigma 2, sigma 3, all of each of the terms are, very finite. And the very fact that alpha s is very small, and if you go to higher and higher order terms, so alpha s will become even smaller and smaller. Eventually, it will become a vanishing. So in that case, for, obtaining a stable and sizable result, okay, we do not have to really go to the, very large number of corrections. So we take, first few terms in the thing. So first few meaning maybe 3, 4, that depends on, how fast the series is converging. So that tells us, taking, fewer terms in the expansion and ignoring the higher terms is what we call as some sort of, asymptotic expansion. And this is true provided the expansion parameter is really small. Had it been very large, then we cannot do it. Or this also fails in the limit where, any one of the corrections, are very large. Or in another words, if alpha s times this thing, or any this combination alpha s square times sigma 2, any such combinations becomes, comparable to 1, then also it fails actually. So there is no guarantee that the series will converge, and each of the, higher order terms are also equally important. But in general, the very basic idea of the perturbation theory is that thing we expand the perturbation series in terms of the, small expansion parameter, and the higher terms can be ignored. So typically, if the expansion parameter is like alpha electromagnetic or alpha weak, so then even alpha electromagnetic square or alpha s square corrections or alpha w square corrections are good enough. Because, if you take the alpha, that is, when I say corrections, forget about what is the, leading order thing. That's not what we are interested in. So in other words, what is sigma naught? That is not what we are interested in. Suppose if alpha is 1 over 137, fine structure constant. Okay, that is already, 1 over 137 is already, less than, 2 orders smaller compared to unity. So then alpha square is even much smaller. A similar argument goes with the electroweak coupling as well. So then these are good enough, provided we assume that thing each of the perturbatively calculable quantities like sigma 1, sigma 2, all these corrections are finite and they don't go drastically, large. So for perturbative QCD, the expansion parameter alpha s is a little bit larger compared to the alpha electromagnetic and alpha weak. So we might need higher terms. So even alpha square is not sufficient. So alpha s cube or even alpha s power 4, as the case may be, the higher order terms are required. But if you believe in this asymptotic expansion, it is not required that you have to go to, alpha s power 5, alpha s power 6. You don't have to go to, very large number of corrections. The series can be truncated after considering a fewer number of terms. So recall that for the case of Higgs production, so where the full, third order correction has been computed way back, around 2013 or 2015, around that time, the full NQ-value result is available. And we see that even apart from the leading order, the third order correction is still, contributing about, 1 or 2, around, few picobarns. Whereas the leading order correction, depending on whether you are working in the effective theory or whether you are working in the exact theory, it contributes around, 14 picobarn or 20 picobarn, depending on what is there at the leading order. Whether you are taking the finite quark mass effects, whether you are taking the infinite quark limit, or whether you are taking the bottom quark contributions. So for whatever be the thing that you take at the leading order, so the leading order contribution is of the order of, around 15 picobar, 15 to 20. Also for a, center mass energy at LHC of 13 TeV. For such a scenario, even alpha S corrections, okay, in the case of Higgs, they are almost, as large as 100% of the leading order. And then alpha S square corrections are still 40% or so of the leading order. Then alpha S cube corrections still, like something like a 2 or 3 picobar. These are not still, negligible, which means, if you want to really measure the production cross section, so this, precision studies are important. Or in other words, what happens if you do not have these higher order corrections? So then we say that thing, whatever we want to compute using the perturbation theory or using the quantum field theory concept, that observable, has, large uncertainties. Of course, if there is a discovery like a resonance, you can say, yes, there is a resonance, there is something new we have observed, but you cannot interpret. In the sense, you can infer the existence of some discovery, but you cannot identify and say that with confidence that this discovery corresponds to the, whatever is the expected standard model Higgs. Maybe it could be some other Higgs. Unless you have the, precise predictions for the Higgs, and that data, matches with the exact theory from the experiment. I mean, as precise data as available from the experiments. Only when you make a comparison, then I can say whatever I have discovered, that is also standard model Higgs. So for that thing, the precision studies are very important. So now attempts are being made even to go beyond the alpha S cube level. So which is like a, alpha S power 4 corrections, for example. For loop corrections are already going on in the context of, Drillian like processes. So once you know the Drillian a little bit, if you believe in the topology, of course, physics says it's different. We can do the DIS like deep energy scattering or the vice versa. Or if you're even clever enough, the ingredients can also be used for the converting of the, E plus E minus goes to 2 jets. All are interconnected, whether E plus E minus goes to Q bar or, quark, photon quark interaction, which is like your DIS type of interaction, or the QQ bar goes to LL bar. All are interconnected to some extent. But when it comes to the, loop calculation, yes, it is true. But when it comes to the real corrections, things are little complicated. So now let us extend it further. So the general formula for head-on level cross-section. So here we give a connection to the head-on level cross-section. So namely that thing, suppose, if you have a process, something like A plus B goes to C plus D. So where A and B are two partons. So here I'm assuming the scenario where we are considering the head-on colliders, and A and B are any two partons, say quark-quark or quark-antiquark or quark-gluon or gluon-gluon. And it is going to some certain final state C plus D. In principle, you don't have to bother about what is the final state, but the final state is something that should correspond to your given final state. It could be a, one particle final state like a Higgs or, on-shell Z boson. Or it could be, multi-particle. It does not have to be necessarily, only two particles in the final state. So all that we know from the quantum field theory techniques is that thing, if two particles are interacting to produce, certain final state, these things we can do using the all these, scattering amplitudes, all the matrix element techniques. Using that thing, we can predict what is the mod m square, the squared matrix elements we can compute, and upon integration over the phase space, available phase space, then we got what we call as at the parton level cross section, which we can simply call this as a sigma hat. So sigma hat, corresponding to the interaction of two partons A and B to give rise to a certain final state. So that is what this thing, and this is sigma hat AB. Once you compute at the parton level, how do you go to the head-on level cross section? That is by taking or by convoluting the parton distribution functions. Meaning, what is the probability of finding a parton A inside the head-on, first head-on, okay, that is carrying a fraction x1, and similarly what is the probability of finding the parton B that is carrying a fraction x2 inside the head-on 2. So when two head-ons h1 and h2 are colliding, what is the probability of observing a certain final state? In this particular case, CD is the final state. So that probability or that particular prediction for the scattering cross section can be obtained from the parton level cross section by convoluting with the relevant parton distribution functions. So here FA and FB. So I'm not beginning with the all the basic level, in the sense I'm not considering the bare parton distribution functions and all the singularities are there. So I hope you are learning a lot of techniques in the loop calculation. We have dealt with different type of singularities, possibly in the same things. Those singularities need to be cancelled from the real emission corrections. So the real diagrams also will have the singularities. So upon cancellation of all the singularities, what is left over is the finite quantity. That's where I'm beginning with. So in that sense, even if suppose all the soft singularities will cancel, and the collinear singularities will cancel if you consider the final state collinearities with the real corrections as well as the loop corrections, the final collinear singularities. But what happens to the initial state collinear singularities? They will not cancel with anyone. So the initial state collinear singularities, there is no other way except, to absorb them into any of the known bare quantities. So that bare quantities in this head-on level scattering process, what we have is the bare parameters are here, the Parton distribution functions. So now if I absorb, those collinear singularities into the bare Parton distribution functions, and I redefine these bare Parton distribution functions as, something called, the factorized thing, or in other words, the renormalized Parton distribution functions. This renormalization is, you can use the word like maybe in the theory as such, you have the UV singularities are there, UV divergences are there. So those divergences, you absorb them into the strong coupling constant and you renormalize the coupling constant. But in spite of that thing, if you have further singularities like soft singularities, and you just ensure whether they will cancel at the amplitude level, meaning at the diagrams level, virtual, real, whether they cancel or not, you can check. Even after ensuring the cancellation of the soft singularities, you can check the final state collinear singularities, whether they cancel or not. Even after that, you can check the initial state collinear singularities. After checking initial state collinearities, if they do not cancel by any means, then the only way is that to absorb them into the bare Parton distribution functions. So this is exactly a phenomena similar to how you absorb the UV divergences into the alpha S with the help of the Z function, and what we call the eventually the renormalization group evaluation comes into the picture, and then you have the what you call the beta function also comes into the picture that decides how the alpha S evolves. Similarly here, instead of the UV divergences, if we have the initial state collinear singularities, we do not know where to absorb them, so we put them into the bare Parton distribution functions, and that process is called collinear factorization because they come in the collinear limit. So now once you once you absorb them, and you can call such a process as a secondary normalization kind of thing if you want. Okay, otherwise this is a simple factorization. In that sense, I am calling them as a renormalized Parton distribution functions, but it should not be confused with the UV divergences. These are purely to do with the collinear singularities. So by definition, so I have the PDFs in this scattering cross-section formula, the formula 1. I have the PDFs which are, which are, already the collinear or the renormalized PDFs. So they also, like the alpha S, how it evolves with the help of the beta functions. So these things also, Parton distribution functions also evolve with the scale mu f, okay, with the help of what we call as the DG-lab equations. So those things in any basic QCD textbook, you can find those details. Right now, this is a general formula for the head-on level cross-section. So let us go to the, further details into the Parton level cross-section. So here is the place where I can connect, the head Parton level cross-section sigma hat AB. So with the, previously defined, the expansion parameter. So the expansion parameter in the case of, our LHC studies, typically we use this thing, in the perturbative QCD, we take the strong coupling constant. So this, whatever the Parton level, cross section, so I can try to predict it using the perturbative techniques by systematically expanding the theory in the perturbation series with the help of the strong coupling constant. Here, mu r is what we call as a renormalization scale, which is introduced while doing the UV renormalization, and mu f is called the factorization scale, which is introduced while removing the collinear singularities in the theory. So then, the equation to concept, we have to clearly use a different definitions. So for that thing, quite often you see a different picturization or different way of writing the equation to. That is, I can take sigma hat AB, and where I can pull out the bond level scattering cross section, Parton level bond level scattering cross section, that sigma naught. If I pull it out, okay, whatever is left over, the higher order terms, okay, so sigma I, in a sense, you pull out sigma naught from there, and whatever is left over is what we call as the Parton coefficient functions. So this is a quite often all of you are familiar with this thing, but the entire idea is that thing, how does this delta I look like? So, and before that thing, we can see some of the examples of what are these, underlying hard interactions. So, for example, if there are two partons A and B, what will be the final state? So, I can take one example. Some of the very well-known examples that all of you are familiar with is like Q plus Q bar producing to a on-shell Z boson, the Drillian process, but only on-shell Z boson, nothing else. Or you can have the off-shell virtual photon or of the off-shell Z boson that eventually decays to LL bar, which we call as the Drillian production. Or if you go to the lepton colliders, the vice versa exactly happens. E plus E minus goes to, we have the Q plus Q bar, or E plus E minus goes to two jets. If you know the perturbation techniques, you can go from one process to the other process easily. So whereas, when another example is, production of two photons, diphotons, or production of, two massive gauge bosons, either two Z bosons or, W plus W minus, or, production of, Z boson in association with the Higgs, what we call as, typically the Higgs-Ströling process, like a Bremse-Strahlung process where a photon or a gluon is emitted from the underlying quark line. So similarly, a Higgs can be emitted from the Z boson. So this is called a Higgs-Ströling process. Or you can have the on-shell Higgs production in the gluon fusion channel, or you can have the Higgs production in the BB bar annihilation. So all these things are colorless particles in the final state. But in addition, I can have the two partons, to give rise to two jets, say J1 and J2. So this is the dijet production in head-on collisions. Or I can have the on-shell TT bar production. Or you can have the, gluon fusion, top pair production in the gluon fusion channel. So what I mean to say, the colored particles, LHC being the, head-on colliders, so all the incoming particles, okay, they're actually colored particles, but the outgoing particles, the particles in the final state can be both colored as well as colorless. So there are some examples of the colorless particles in the final state system as well as colored particles in the final state system. In both the cases, you can calculate the parton level cross section and expand that thing in terms of the strong coupling constant, so that perturbation theory works. So consider, for example, a simplest trivial case. Okay, a Q plus Q bar goes to Z. Or here is a place where we try to introduce some momentum convention as well. So let us say the initial parton coming with a small momentum P1 and a Q bar coming with a small momentum P2 and giving rise to an on-shell Z boson that has a momentum Q. By definition, on-shell Z boson meaning the Q square should be equal to mz square. Or in another example, a gluon fusion. Hello.
Yes, sir.
Yes, sir, we can hear you.
Any questions?
No, not yet.
Okay. So in the gluon fusion channel, you have the Higgs production, for example. So where a gluon with a momentum P1 and another gluon with a momentum P2 can give rise to a Higgs, on-shell Higgs, just on-shell Higgs. So in that case, Q square will be, it is a mh square. So what about this, Mandelstam variables that we calculate? So P1 plus P2 whole square is the, total square of the incoming energy, which is, what we call as a ECM square, that is equal to small s, is nothing but P1 plus P2 whole square equal to Q square. And now this P1, small P1 plus P2, I can express in terms of the head-on variables, head-on momenta, capital P1 and capital P2. So in terms of these fractions, momentum fractions, x1 and x2, also called the Bjorken variables. So when I expand this thing, and if I take the high energy limit, basically, capital P1 square and capital P2 square. In the case of LHC, these are like a mass of the protons, which is like a 1 GeV. You can, you can happily ignore them. So compared to the 13,000 GeV, you can just ignore in the high energy limit, the masses of the hadrons can be ignored. So in that case, it simply turns out to be, okay, so the P1 plus P2 whole square, capital P1 plus P2 whole square equal to 2P1 dot P2 simply, which is what I call as a capital S. So the small s is related to the capital S by this connection, small s equal to x1 times x2 into capital S. So now for on-shell Z production, what is this S? So S equal to x1 times x2 times capital S equal to Q square. And for on-shell Z boson, this Q square equal to mz square. Whereas for on-shell Higgs boson case, on-shell Z boson, it is mz square. For on-shell Higgs production case, it is a Q square equal to mh square. So now at the lowest order meaning, so at the parton level cross section, the entire incoming energy P1 plus P2, where P1 is the, four momentum of the quark and P2 is the four momentum of the anti-quark, or in the case of gluon fusion, P1, P2 are the four momenta of the incoming gluons. So this entire four momenta for the on-shell case should exactly convert to the, your given final state momenta. So just exactly the on-shell. So there is no other, violation of the momentum. So in that case, so I can define some quantity called the small z, which is equal to mz square, meaning basically q square by s, which is equal to mz square, or small s, I can write it as a x1 times x2 times capital S equal to, I can pull out 1 by x1, x2, and this entire quantity mz square by capital S, I can call this as a tau quantity. So this thing Z is, related to the small x1 and x2 by this definition. So quite often, people, many times they use this thing Z, x1, x2, tau, and they, quite often they interchange, they write Z equal to tau into x1, x2. It is not correct always. So tau is the smallest that you have in your calculation, in a sense. So x1 and x2 have to accordingly adjust it. So this is the situation. So for for a given mission, meaning proton colliders like LHC or proton antiproton colliders like Tevatron, once the capital S is fixed and once your final state system that is also fixed, whether it is mz square or mh square, automatically the tau is fixed. What is not fixed is, the center of mass energy at the parton level. What is the center of mass energy at the parton level? That is small s. Because this momentum fractions x1 and x2 are keep changing, whereas capital S is fixed, the small s is not fixed. And since small s is not fixed, as a result, the z is also not fixed. So the z, x1 and x2, these are like a dynamical variables. So at the leading order, exactly what will happen is that thing. So this z equal to exactly 1. There is no other way because all the momentum are fully constrained. But however, at higher orders, where additional parton radiation can carry some energy, the scenario looks like, in terms of the momentum conservation, it looks like, you have P1 plus P2 goes to Q plus P5, where Q is the, the four momenta of the on-shell Z boson or the on-shell Higgs boson. And what about P5? P5 is the energy of the additional radiation that is going out of the system. So in the case of, Bremsstrahlung radiation, so this P5 corresponds to the four momentum of the gluon. Or in the case of other subprocesses like a QG case, etc. So the P5 corresponds to the energy four momentum of the quark in the final state. So that is what we call simply P5 is the four momentum of the radiated part. In that case, certainly you cannot have P1 plus P2 equal to exactly Q. P1 plus P2 is greater than or equal to Q. So which means that thing automatically when you square it, S is much greater than, S can be, definitely has to be greater than or equal to mz square. Whereas, if you have an additional radiation. Equal to 1 is also possible because the additional radiated parton, can have a zero energy. Like a gluon can have a almost, negligible energy, but it can still be radiated. In that sense, the greater than or equal to is coming. Whereas if the radiated parton is having a large energy, S is definitely greater than 1. So, because S can be greater than or equal to mz square, automatically the small momentum fraction that we defined, Z equal to Q square by small s, that Z is automatically can be less than or equal to 1. So this is a crucial difference when you go to the lowest order and you go to higher orders. So at the lowest order you have Z equal to 1 exactly, whereas at the higher orders you have Z is less than or equal to 1. Z can be equal to 1. That is also possible at higher orders. So Z also can be less than 1. So here Z has information about the fraction of incoming energy. So what does it actually mean? Incoming energy is root S, or S carried away by the final state observed particle. Suppose if there is a capital, small root s is the total incoming energy. A part of that system is carried away by your observed Higgs or observed Z boson, for example. And what about the remaining energy? And that remaining energy, which is the fraction of the z times s is carried away by the your final state system, say z into s equal to mh square or mz square. What about the remaining energy 1 minus z? That 1 minus z has the information about the remaining energy carried away by the additional parton radiation in the final state. So this is simply in terms of the kinematics. So as such, there are no dynamics in the scenario. So in terms of this z variable, we can write the partonic cross section once again. We look into the parton level cross section when we expand, using the asymptotic expansion. If I want to write the sigma hat, which is a function of your observable final state mass. So in the m square is the mass of the Higgs. M is the mass of the Higgs for the case of Higgs production. M is the mass of the Z boson for the on-shell Z boson case. So this parton level cross section for the production of a on-shell Z boson or Higgs production case, as the case may be, can be written in terms of the sigma naught, which is the leading order process, times all the higher order terms. I can make it in terms of in this series expansion form. So here the AS, I have introduced one quantity. AS is nothing but alpha s by 4 pi, and alpha is related to the standard GS squared by 4 pi, the strong coupling constant. So for simplicity, I'm dropping all the arguments like the mu r. So by definition, all these quantities on the right hand side, they are calculated in the perturbation theory. So they all depend on the mu r, the renormalization scale. These are, as of now, these are at the parton level. So you can also have the head-on level cross section. So in that sense, on the right hand side, the mu f dependence also comes into the picture. So now the perturbative coefficients can be conveniently expanded. So here this is the one. This is all that we can calculate, either for the case of de Leon production process or for the case of Higgs production process. And this delta I is what we call as the coefficient functions, is what we need. Once we know the leading order contribution, you just pull it out, and whatever is left over, the parton coefficient functions, which are dimensionless quantities, because Z is a fraction of the energy, so which is a dimensionless quantity, and your coefficient functions depend only on the Z. So this is a completely parton coefficient functions. They do not have any dimensions. All the information about the scattering cross section or the kinematic distributions, all the units, everything is encoded in the sigma naught itself. Now what we calculate from the parton perturbation theory point of view is this delta I. I stands for the order of the perturbation theory. So for example, at the higher order, at the first order, this delta 1 of Z, okay, if we expand it and compare, look at the known results. So this is how the typical structure looks like. Here, I'm just, going a little bit faster because, I did not mention about, how you calculate these things. For the 2:1, it is a trivial thing. Still not that trivial when you go to the higher order corrections. But however, for the 2:1, what you can do is that thing using the phase space mapping, you can convert the entire phase space radiation, phase space integral in terms of the these fractions of Z. For that, if anybody is interested in, please go to this Willifan Nirvan paper, the way back, very early papers, 2000s or so. So where, he has studied about the de Leon cross section at n square elbow. So whether it is a de Leon case 2:1 type or, 2:1 Higgs type of production, the phase space, same phase space applies here. Later, instead of calling that q square as the invariant mass of the one particle, you can extend that idea as if you have final state observable quantity. So that is something interesting when it comes to the kinematics point of view. So, but you can see here, so this delta 1 of Z, I can expand it here as a function of this curly D1 and curly D0 and Dirac delta of 1 minus Z. As I said before, the delta 1 minus Z at leading order exactly Z equal to 1 is the situation. Z equal to 1 corresponds to leading order, or in other words, leading order corresponds to Z equal to 1 limit. But at higher order also there are limits where z can be exactly equal to 1. Meaning that kind of situations correspond to the type of graphs where if you have a real radiation diagrams where the real gluon completely becomes soft or exactly collinear as per the configuration is considered, or it corresponds to loop corrections, purely loop corrections to the underlying bond scattering process. So in that sense, at every higher order also you have the z equal to 1 configuration. Plus you have a z is not equal to 1 configuration, and that z is not equal to 1 configuration has a broadly speaking, two different type of contributions. One is what we call as a curly D type of contributions. Other is what we call as a regular corrections. What are these curly D type of contributions? And before we go into these things, these are like a curly D type of distributions are like a plus distributions. Okay, similar structure you can also see at the second order in the perturbation theory. In the second order coefficient functions also can be expanded in terms of these curly D's. Okay, the plus distributions, as well as some other regular function what I call as the R2, as well as delta 1 minus z. You can ask this at least one beautiful question without going into the structure of the curly D of 1 minus z. If you have a direct delta function, delta of 1 minus z, which is a singular, or if you talk strictly in the mathematical sense, it's a highly ill-defined. How does it make sense? Okay, I can have a partner level cross section where there is delta 1 minus z, which is like a singularity. How does it make sense? So it simply makes sense. Hello.
Now, if anyone has question, then they can ask.
Yeah.
Yeah. You wanted to ask a question, right?
So in the previous slide,
Yes.
Okay.
yeah, when you wrote this formula in the green color, so is it always true? Like so, sort of factorization I could actually imagine here.
Here you can do I think this sigma is right. Sigma is just a linear quantity.
Yeah, yeah.
So if you can go back here, you can go back here. Here the same thing is right, or even further, we can go to this side. This is the side forward, right? What you can do that in this sigma is a high quantity, you can just pull it up.
I see. So this is not.
You can just pull it up. That is multiplied by this side. And what you do that for the coefficient functions.
Thanks.
Okay. In the next way, I am talking about it.
Any other question?
Sir, what is R1 of Z, what you are writing at the final, I mean delta phi?
Which is
Page number 4, I think. If you go at the end of the page, 4 or 5, I think. So, what you are writing this delta equal to, I mean D10, yes, this part.
This
so,
one, okay.
Yeah, so what is R1 Z?
This curly D1 and curly D0, these are the ones I am telling you. The definition of any curly D is this thing. Okay, so these are the structure dependence. Okay, log of 1 minus z by 1 minus z. Okay, so you can ask basically in terms of the can you tell me what is the integral of 1 of x?
Log of x.
Log of x. So integral of 1 minus z is log of 1 minus z. So if you take the log of this thing, if you go to the in the higher possibility, even in the higher cost of the logarithms. This will be clear when you go to the median transformation. But here what does it mean actually exactly? So there is a dependence on the z, which also z equal to 1 there is a problematic this here. Okay? Z equal to exactly 1 corresponds to even at the higher order corrections, okay, meaning at n0 level or at n2 level, you have a configuration where z is exactly equal to 1, which corresponds to exactly loop type of corrections, or you can have a exactly soft gluon radiation limit or exactly collinear gluon radiation type of limit. So in the exact z equals to 1 limit, exactly z equal to 1, not in z equals to 1 limit, z equal to 1 case, you have a similarity. And that similarity has got cancelled by adding the real and virtual diagonals to each other. So the pole is actually removed. Okay, but that time you can also look at the, by taking it over the, a propagator. Suppose imagine you have a port line, which is emitting a soft blue one. And after the emission of the soft blue one, you look at the remaining propagator, port propagator. Okay, so then you can see the limit that goes to 1, it also goes to the on-shell limit actually. So which goes to like some sort of similar behavior is there. The exact similarity is compensated with the virtual, similarity, coming from the loop diagrams. But in the limit that goes to 1, it slowly goes develops a logarithmic structure, and that is what is behavior. And when the similarity is there, the pole is removed. But the logarithmic nature is that is what is still left over. And that is what the combined logarithms. In the sense, that is the exact meaning that z equal to 1, the pole is removed. Okay, so that is a very important point to note here. In other words, z equal to 1, it is a finite. It is not an infinite thing. So the definition of the plus distribution or the curly react is the following actually. If I take any plus distribution, and I compute it with respect to the any other functions. For example, here, okay, the entire function will coming as a Poisson coefficient functions. Okay, but this entire Poisson short circuit I have to convert it with the Poisson distribution functions. So this is something which is a very defined quantity. So while converting with that thing, I can define this thing. Suppose without going into the details, if I have any general plus distribution, I'm convoluting with another smoothly defined function z of z. So the way we define the plus distribution is that thing, this is the thing. So you remove the plus, act f of z on g of z minus g of 1. So in the limit z equal to 1, right at z equal to 1, the pole, whatever the pole that you see in the f of z, that gets exactly multiplied by 0.
Kumar. Hello.
Yes.
Yeah. So why this series actually started from D3?
Why this series?
I mean, this delta 2 is started from D3, and you have some coefficients. So
this is just calculation. You can calculate it. Let's say this is the observation for the no processor so far. Okay, you can say this kind of thing. You can the best way of putting this thing is working if you go to the Mellin space. Okay, so this curly one, I can call this as a Mellin logarithm. Okay, they go like a log square, one power higher. If you have the curly okay, in the Mellin space, the highest log that you will get it is log I plus 1. Okay, so in that space you can have a better picture. Okay, so then if you take the first order, and the first order meaning only one real gluon emission is there. So that emitted gluon can be both soft as well as a cooling here. So you can have a double enhancement. So that is what is seen as like a log square kind of enhancement. And when you go to the second order, you can have two such logarithmic enhancements. So it can be like a Mellin n forward, this is a log power 4n. Which I compared with the Z space, which is one less, so that is the curly thing. In that way you can visualize and interpret it. I hope that answers your question.
yeah. Thanks.
Okay. So then we come to the first order correction and the second order correction. We have something called the R1. What is this R1? R1 is a regular class I'm talking about. Meaning anything which does not have the this type of Dirac delta function or this type of curly D contributions. So what does the structure of this regular corrections look like? Regular corrections look like log of 1 minus z or 1 minus z into 1 minus log of 1 minus z, or you can have some simple polynomials, some simple polynomials involving like a z square plus z cube plus z minus 1, etc. This kind of thing. Or for that matter, in the when z is less than 1, mod z is less than 1, the z highest value is 1. When z is less than 1, you can make the log 1 minus z also. You can make an expansion. Mathematically, you can expand around, you can expand in terms of z. So that also contributes to like some sort of polynomial. Okay, so that is the main thing here. So now all these things, these are what we call in this particular, what particularly I insist on the threshold resummation, the dominant logarithms are these things. Okay, that's what I put it here. And the less dominant contributions, that is where I call them as, regular corrections. Those regular corrections also can have some sort of, but somewhat, less dominant logarithmic contributions. Compared to the, the curly D type of contributions, these logarithmic contributions are somewhat suppressed. Okay, they are not very dominant, so that's what I can keep them separate. These are not very significant in contribution. So, but we have a different understanding now. I mean, things are evolving with the time. So, people are also trying to call, yes, this kind of logarithms are also important. What we call is, this is some sort of, beyond threshold logarithms. So all these things, if you see, the curly D type of contributions as well as delta type of contributions, right in the Z goes to 1 limit, they are significant. So Z goes to 1 limit in that sense is very important. So I come back to this thing. So clearly the curly D of Z are large in contribution, particularly in the limit where Z goes to 1 limit. Z goes to 1 limit meaning the Z is defined by Q square by S, where Q square is the total mass, the square of the mass of the final state, meaning how much is what fraction of incoming energy is carried away by the final state system. And if the entire fraction goes to 1, meaning whatever the total energy is being converted into the final energy. So that is what is the threshold limit exactly. So at any given order, we can write the Partonic coefficient functions as, delta I of Z. For any, here I gave the example of, 1, 2, etc. But if I take, delta I of Z, okay, here I can write it as a Ci 2i minus 1 delta 2i minus 1 of Z, and then you keep on decreasing. It goes all the way up to Ci 0 delta curly D 0 of Z, and then Ci delta of delta 1 minus Z, plus the regular term at that order, where I can be the order of the perturbation theory. So it can be 1, 2, 3, etc. And all the ones that are there, denoted in the red color because of, presence of the, this large logarithms as well as a Dirac delta function. These by definition, somehow, they're called the soft virtual terms or soft virtual corrections. And delta 1 minus Z comes exactly in the absolute soft limit as or in the virtual limit. All other remaining things are close to the soft and collinear limit. So though it is a soft virtual, the collinear contribution configuration is also encoded in there. So these are what we call as a soft virtual or threshold limit. And then any other corrections beyond SV, meaning in the limit where Z is less than 1. In the Z is less than 1 in the limit. So these curly D distributions may not be very large. Also Z equal to 1 does not correspond to that region. So that is the region what we call as, simple regular functions. They do not have, complicated structures. They will not also give large contributions. So these are called the regular corrections. So broadly, this particular, Parton coefficient functions, I can simply write it in two pieces. One is what I call as the soft virtual corrections. These are the soft virtual corrections that I have talked about. And any other thing, Ri, this is what I call as the regular contributions. So this is the, broad, structure of the, perturbative coefficient functions. Now here comes the very important points. And once you understand, maybe we can break for today. What is the Z goes to 1 threshold limit means actually? For that, let us take a simple thing. For example, Higgs production case at 13 TeV LHC. So let us write everything in the GeV case. So your S, capital S, the center mass energy in the head-on level is 13,000 square, and mH for the Higgs production case 125 GeV is the Higgs mass, so it is 125 square. And x1, x2 are the Parton fractions, so they are always less than or equal to 1 by definition. So the fractions can be maximum 1. Okay. So and your limit S equal to the Parton level S equal to x1 times x2 times capital S. And in this case, clearly, okay, if you want to produce a Higgs boson at LHC, meaning your Parton center mass energy definitely has to be greater than mH square, because that is a basic kinematic requirement. And this small s is a variable quantity and it can go as large as capital S. So this is for a kinematically allowed process, this is the entire region that small s can take. So now for any given center of mass energy, the capital root S is fixed and kinematically, it should be greater than your observable quantity. So root S has to be simply greater than or equal to mH. So which implies that thing, okay, so capital S is always greater than mH square, but S can vary anywhere between that thing. So which means that thing there also exists a limit that small s can be closer to mH square because these momentum fractions, they keep varying from 0 to 1. 0 to 1 subject to the condition that small s equal to x1 times x2 times capital S. So in that case, there exists also limit that root S, the total energy of the incoming partons is just sufficient to produce your given final state mass. So that is what we call as a Z goes to 1 threshold limit. In that case, what is the amount of energy that is left for the radiated partons? If at all there are any gluons, so that there is hardly any energy left. So in that sense, in that limit, the gluons, radiated partons have to be essentially soft or cooling here. So the energy that is sufficient, okay, just to produce a given final state is what we call as the threshold energy. But there also exists, this is not the only limit. S can vary the entire span. In this limit, so S can also be much, much greater than mH square, which in other words, the small z can also be much, much smaller than 1. So z can be close to 1 or z can be far less than 1. Both limits exist in this situation. So because of this thing, there is a tight interplay, which normally, you will not find quite often in any obviously, in any discussions. So that is the interplay between the parton fluxes and the parton coefficient functions. This is a very, very important thing. So if you take the root S equal to 13,000 GeV and MH equal to 125 GeV, let us take what is the corresponding tau value. Tau value is 125 by 13,000 whole square. So this number is something like, you just calculate for yourself. It is around 9.24 into 10 power minus 5, which is roughly 10 into 10 power minus 5, which is like a 10 power minus 4. So tau quantity is very, very small. Whereas corresponding to the same process, Z can be anywhere. Z can be Z can be as small as 10 power minus 4, but Z can also be greater than, close to 1. The x1 and x2, similarly, they have to follow the relations. So tau equal to x1 times x2 times z. That is the relation they have to follow. And now tau we have found for the Higgs case, and we also have the relation that z equal to tau by x1 x2, or equivalently small s equal to x1 times x2. And now here is the main important point. Z enters the parton coefficient functions and x1 and x2 enters your parton distribution functions. Okay, so here the way I have written the head level cross section after pulling out the parton level bond part after pulling it out. So you can have this, parton level coefficient functions delta of z, all the parton level contributions, okay, which can be expanded as a series in the perturbation theory. But these things, parton level coefficient functions, they need to be convoluted with these things. Subject to that thing, there is a condition that x1 times x2 times z should be exactly equal to tau. So that is roughly in this particular case, we have seen that is something close to, 10 power minus 4. So this kind of relation it has to satisfy. Now the question is that thing, even when z equal to 1 limit, okay, even when z equal to 1 limit, tau for this given observable corresponds to smaller values of x1 and x2. For example, you take this same case, tau is very, very small. Now, even if I take z equal to very, large value, possibly larger value. So z equal to 1 limit, if I take x1 and x2 takes very, very small values. But x1 and x2 smaller meaning the corresponding momentum fractions are very small, meaning there is a high probability that you can find such a parton inside the hadron. Meaning obviously the corresponding parton fluxes can be much, much larger. That is decided by the, the tau value actually. The tau decides, what is the region, what is the contribution of the parton fluxes. Notably, if you understand this thing, this parton distribution functions depend only on the fractions. It does not depend on the absolute energy. Whether you are working at the LHC or at Tevatron, so for me it is not important whether I'm producing the, mz square or mh square or top mass square. That is not what is important. What is important is this particular fraction, or in other words, this tau is what is the most important thing. If tau is a smaller, the corresponding fluxes are much, much larger. So the PDFs corresponding to this region of small x1 and x2. So in this relation, you put z equal to 1, what I call as a threshold limit, you put it there. Even then, x1 and x2 should be corresponding to the 10 power minus 4. Meaning, x1 and x2, if x2 is as large as 1, then x1 is, very small, like 10 power minus 4. Okay, then the Parton distribution function value is very large, but x2 will be very small. But if you take the ideal situation, somewhat, intermediate situation like 10 power minus 2, so even in that case, the PDFs are very, very large. So as a result, there is a tight interplay between these things. So otherwise, so far we have been discussing what is the contribution at the Parton level, whether, regular corrections are large or the, other, beyond regular, non-regular corrections, namely the soft virtual terms, whether they are large. We are just looking at the logarithmic structure or the delta 1 minus z structure. But what is getting multiplied in front of what is getting convoluted with these coefficient functions is what is more important here. So that is the fluxes that we have into the picture. So more importantly, the flux phi of tau corresponding to the tau equal to 10 power minus 4 region is the most important region. I will show towards the end one flux plot. How does it look like? So once again, here we have for every tau there exists a z equal to 1 limit, and the reverse, that is for z equal to 1 limit does not imply tau equal to 1 limit should exist. Okay. So that is the most important. That's quite obvious. For example, you have seen here. So for the case of at LHC, capital root S equal to 13,000, MH equal to 125 GeV. Tau is much, much less than 1. Okay. But Z can always exist. But Z equal to 1 doesn't mean tau has to be 1. Okay. But tau equal to 1, why that is important? Tau equal to 1 implies, okay, the Parton fluxes are very, very small. Tau is small, far less than 0. Tau is closer to 0, meaning the Parton fluxes are very, very large. So what about the Z? What about Z less than 1? So far we are talking about two regions, okay, when Z equal to 1 case only. When Z equal to 1, what is the corresponding tau value? Tau is always fixed for the given final state and from the given mission energy. Tau value is always fixed. And in that case, when Z equal to 1, what happens to the x1 and x2 values? Based on that thing, we are interpreting the contribution coming from the Parton fluxes. What about the region when Z is less than 1? Meaning the region where the threshold logarithms are not important. So that Z less than 1 or Z far less than 1 limit, this is the limit in which, soft virtual terms need not be large. Okay. And R of Iz are always finite. Okay. So there is some sort of interplay. That is the region where it is very difficult actually to say which contribution is very large. So you have to calculate, but unfortunately, there is no mechanism to find out because, all this Z, these are, at the Parton level they are happening. So you cannot experimentally measure. All that you can do is that you take these kind of, curly D contributions, the regular contributions. Mathematically you can plot and then see which contribution is more in which region of Z. So all in all, okay, there exists variety of different regions of Z. Okay, so the limit tau less than 1, okay, for less than 1, like the case, 10 power minus 4 for the Higgs production, or even much less than 1, like mz square by capital S for the case of Ornstein Z production. Tau is much, much less than 1 implies the fluxes are very, very large. And that region can have two different configurations where Z can be close to 1 or Z can be less than 1. If Z is close to 1, meaning the soft plus virtual corrections are dominant over the regular corrections. Whereas Z is much less than 1 means soft plus virtual corrections need not be large and can be compared to the regular. And it is also important to note that thing, the regular corrections, you have a type of terms like a log of 1 minus Z. For example, I'm just giving a simple example. This log of 1 minus Z when Z is less than 1 is the entire argument is less than then. Okay, obviously it is like a log 10 power minus 1 or log of 10 power minus 2, which is a negative number actually. So quite often you can see the regular corrections, sometimes they can be negative in nature. If you are if you want to know a little bit more, you can see the recent Drelian NQ paper, where you can see in certain region of the kinematic region, the third order correction, overall third order correction, okay, is some sort of negative thing. Okay, but the total cross section is positive. First order corrections are positive, second order corrections are positive, but for the Drelian invariant mass distribution in certain region, okay, the regular corrections are very important, and they are such that the total third order correction has become a negative quantity. Of course, you cannot simply rely only on the regular corrections. There are also other parton channels, namely the QG and QQ bar, QQ. Other channels are also important. But so when you go to sufficiently large value of Z or large value of tau, the respective parton fluxes keep falling down very sharply. So around Z equal, around Q equal to 800 GeV or case, for the case of Drelian case, what people have noticed is that thing, okay, the regular corrections or the overall third order corrections can be negative, which is some sort of, very important thing. Also, just, in this matter, I also like to highlight one thing. Way back in 2014, I think Professor Ravindran team, they have done a nice work, and, they have done before that thing, the Drelian, regular corrections, okay, the full one loop part is not available. So when that part is available, they compared with the known threshold corrections without the delta 1 minus Z, and they have included the delta 1 minus Z. So the entire effect of adding all the curly D contribution at the third order, if it has a certain magnitude, the same contribution of delta 1 minus Z is coming from the same magnitude. So this is also interplay between the different logarithms at this order. So it is not just, you look at one particular curly D1. Say for second order, I just want to show here. So yeah, at second order, some curly D3 is very large. I cannot say entire soft virtual is very large, because you also have to see what is the curly D2 contribution, what is the curly D1 contribution. Sometimes it is a large positive number, but it can be a negative number. And again, it could be positive actually. If that is the way, one is positive, other is negative, one is positive, other is negative, and eventually, all of them, all these curly Ds will add up to a simple number, though individual curly Ds are very large. So there is a trick that we have to. So the perturbatively calculable quantities are very, very important in this thing. Namely, the coefficients that are sitting in front of them, those are very, very important. And at the end of the day, it may so happen that the contribution of all the curly Ds, roughly comparable to the just delta 1 minus Z alone. And even in such case, if the total curly Ds and the delta 1 minus Z, if they differ in the opposite sign, the entire result, is a dramatic situation. This kind of situation is noticed in the, Drelian 3-loop level corrections. For that, please, you may please refer to the PRL paper by Professor Ravindran group way back, written in 2013 around. So then I come back to this thing. So I just mentioned this point, to highlight this thing, okay, that, Z goes to one limit is the delta soft virtual limit. In that case, delta SV terms are important, but Z less than one limit, okay, is a limit where, the delta SV terms may not be large, but that is also the same region where the regular corrections are significantly important, okay. So they can balance with each other. The entire perturbative result at that order also equally depends on the regular corrections. But this is at the perturbative level. Now what happens, another interesting scenario is that thing, if M square is very, very large, so far I am considering M is the mass of the Z boson or mass of the Higgs boson. So if mass of the Z boson or mass of the Higgs boson, if I have considered, these are like 125 GeV or 91 GeV. But for example, if I consider a situation like a Drelian type of process, okay. So in a Drelian type of process, what it has is that I can consider the invariant mass as the mass of the entire transistor system that is carried away. So if the invariant mass is very, very large, then the tau goes to one limit comes into the picture. Tau goes to one limit, or tau goes to close to one limit is the limit where the partner classes are very small. So this is the region where essentially all these parameters z, x, y, they are also supposed to be very, very close to 1. So x very close to 1 implies partner classes are supposed to be smaller, and z close to 1 implies essentially the delta xp are very large. Now this is important. So this is the important configuration where the partner classes are very small, but threshold algorithms are large. So that is the case where if you look at the rectangular cross section, you can safely ignore the complete contribution coming from the regular corrections, because they are simply smaller numbers and they are convoluted with the PDS. And in the large towers to 1 limit, the pattern classes are very small and you can ignore the regular corrections in the large tower limit. Okay, provided we are considering the reading of the channel, which is a very, very important meaning. For the reading case, we are considering only the PQR channel, and the new channel, we are considering only the new fusion channel. But if you take other processes, the situation is again different. Actually. So we are considering a small region all in order to speed. So the comes to 1 limit, or it does not have to be really close to 1, but it is something from smaller value close to 0, and as they are slowly increasing, that is an interesting region where the softless virtual corrections are very important and where the regular corrections can be ignored. So based on this region, that is the place where it is a very difficult task. So the regular corrections which initially I said, they can be comparable to the softless virtual, which are neglected now. So now, how do you rely on the validity of the configuration theory? So the most important information is that these regular terms are highly process dependent, whereas in the delta SV, that is in the z equals to 1 limit, softless virtual corrections are almost process independent. In the sense, if you look at the z equals to 1 limit itself, the radiated gluons either they can have the soft limit or the collinear limit. In that limit, you can just separate that splitting of the soft gluon from the parent quark or parent gluon, or including the splitting nature or the soft nature. You can just pull it out that information. It does not enter into the bond level process. So in this sense, we can factor out that information. So what are the phenomena you are considering? The nature of the soft and collinear gluon emissions. You can simply quantify just by casting a colored particle, a colored quark or a colored gluon that is just emitting a series of n number of soft and collinear gluons. So that phenomenon we can quantify what we call as the first collision or the soft collinear region. So that entire contribution we can pull it out, and what is left over is just only the bond interaction. So the other important thing is that delta regular can be negative or eventually or equivalently they can have a sign opposite to that of delta SV. So the composite limit, what is it? So for this, let us understand initially I said n square is very large. What is n square is very large is something like a Gaussian process. So you take a high invariant mass limit. In the high invariant mass limit, okay, z is essential because composite to 1 limit is the important limit. So then automatically because of the relation tau equal to z into x1 into x2. So the composite to 1 limit automatically implies z has to be equal to 1. So we are essentially in the soft limit. But that is the limit where fluxes do not have to be very large. Now here is the game where you have to see. If you go to really large value of tau equal to exactly equal to 1, the fluxes are almost 0. If the fluxes are 0, there are no events that can be measured. Or that can be events, the cross-section is that the admiral is completely 0. If the tau is far less than 1, the pattern fluxes are important because they are convoluted with the regular pieces. So the regular contribution also very large. So the intermediate region is the most important region. So how you define the composite to 1 limit depends on your experimental ability to measure. But of course there has to be some few events to be produced. In the composite to 1 limit automatically implies the x close to 1 limit. The pattern fraction x. So here I want to just stop it because it's almost 3:30. So what is the reformation here? So consider the case where z equal to 1 is applicable, such that alpha s, okay, at any given order, at nth order in the calculation theory, you have type of terms alpha s into curly dz, and where j equal to, it goes all the way 0 to 2n minus 1. Okay, this way. If any of these terms, okay, alpha s times d of j becomes of the order of 1. Now the question comes, what is the validity of the perturbation theory, or particularly what is the validity of the continuation of the perturbation theory? That is the right question to ask. So what we begin with the, initially if you begin, that's where I said, the expansion parameter, the coupling constant has to be very small, and you can take the asymptotic expansion, meaning taking few terms. Now if any one of the term in the perturbation theory, it becomes, very large. And that is also the sort of, universal, in the sense, if it happens at one order, the same thing can happen at a higher order. The similar pattern repeats. If that is the case, whatever the contribution we see at nth order, the same pattern comes at the n plus 1th order. So, if at nth order there was a contribution which is of the order of unity, at n plus 1th order also that contribution will be there. So, 1 is not smaller compared to 1. So, you have to, take into account all such contributions to all orders in the limit, to all orders in the perturbation theory. So, which essentially means that there is no guarantee or no reason to believe that the perturbation series converges. Okay, it is in the present scenario, whenever this thing happens. So this is more and more important for the case where, alpha times the regular contributions is small. Because, when the regular contributions, their value is also, negligible compared to the softness of your corrections. Because of, relatively, smaller suppression of the quantum flexes, the entire thing is dominated by this virtual region actually. So now, what is the guarantee that the perturbation theory converges? So that is the place, we have to consider not only few terms in the perturbation theory, but I have to consider at least a class of the terms, like this curly T type of contributions, or the soft plus virtual type of contributions, to all orders in the perturbation theory. And we have to sum them to all orders in the perturbation theory. That we necessarily have to sum out all such large logarithms in the perturbation theories, and that we cannot rely simply on the asymptotic expansion. And that is the main motivation of what we call as the, resummation. So if you look at the original, I think the original papers on the resummation, they will not say that actually does not say resummation. They say summation of the large logarithms, something like that, to all orders. So that is what the original resummation paper looks like. So this is the typical class that we are talking about. So tau equal to here q squared by capital S. So the tau highest value is like a 10 power 1. So that is what it looks like. Just do not take this rough sketchy plot. But if you want to see, can you see the figure, all of you?
Yes.
We can see.
Yes, come on.
Yeah. So this is the one, if you see here. So this is the case I have plotted the flux corresponding to the QPR fluxes and QG fluxes and GG fluxes. QPR fluxes are important say for processes like a gradient production. Blue fluxes are important for processes like a Higgs boson, Higgs production. Okay. So now you can see what is plotted on the x-axis is the Q, the final state invariant mass. If you take Q squared by S, that is essentially equal to tau. On the y-axis, what is plotted as the flux. Now here is the important region that I am talking about, the interplay between the quantum fluxes and the quantum coefficient functions. So for example, if you go to the tau goes to, that limit, 10 power minus 4, say something close to the Higgs threshold region. Okay, Higgs mass NH equal to 125 region. So that corresponds to 200, 400, 600, 800. So something, between these two regions. Okay, something closer to this region. Now you can see the corresponding to that thing, the green colored gluon fluxes. How large these are there. So in this large, now you can see this is the tau goes to not 1. Tau goes to 1, limit is not the applicable limit. So actually, the Higgs mass is not in the head. Electronic threshold region. This is far away from the electronic threshold region. Then, what is the reality that why we have to do the resummation? This is a question people quite often ask this thing. That is where I have to interpret, different reasons that is possible. Even in the tau less than 1, much less than 1 region, you will either z equal to 1 region or z is less than 1 region. Z is less than 1 region is the region which is important for the other non-SP contributions. Okay, the regular corrections. Now for the regular corrections, you see what is the important significance of the Parton flux. Yes. And what about only the z equal to 1 limit. So even for tau less than tau equal to 10 minus 4, there is a z equal to 1 limit. And the z equal to 1 limit is the region where the softless virtual corrections are important. But we have softless virtual corrections, but we also have the regular corrections. Regular corrections are important, but softless virtual corrections are also important because of the logic fluxes. So that is the way. Now if you go to the gradient type of invariant mass distribution, say all the way up to 3000 GeV, maybe which is the current experimental limitations, we have seen some events close to 3000 GeV also. Okay, invariant mass distribution that has been probed up to the current LHC experiments, namely CMS and RETLAS. So if you see the events around this region, now you see this at this region, the Partonic softless virtual corrections, they are not negligible. But the Partonic regular corrections, they are simply finite and they are suppressed by these fused Parton fluxes. And that is the reason though Parton fluxes may not be large, but the Partonic coefficient functions are becoming very large and large. And z equal to 1 case. So that is the case, if you really push the z equal to 1 limit, the regular corrections, they are simply, finite, and because of the falling Parton fluxes, they simply kill, and there is no contribution that you can expect from the regular corrections. But whereas because of the rising, large logarithmic contributions, if you really push tau to 1 limit, the perturbation theory at any order breaks. If you manually plot, Q goes to all the way up to 13,000 GeV, and you can see, there is a tricky interplay. Suddenly these things keep looking like they are falling down, and suddenly the Parton coefficient function they just blow up. Meaning that is a validity, that is a breakdown region of the perturbation theory. So that is the case, we cannot just rely on one particular fixed order result. So rather we have to consider the effect of all fixed order results. Meaning we have to consider the results to all orders in the perturbation theory. So at least that is the game where you cannot just rely on the perturbation theory, you have to do the resummation. So that is the whole motivation. This is a case where I am talking about the threshold region, meaning if the Brilliant invariant mass takes huge amount of energy, invariant mass takes 10,000 is the Brilliant invariant mass. So whereas the hadronic center of mass energy is like 13,000. So 10,000 of the total energy is carried away by the final state system. So the amount of energy that is left over is very small actually. So as such, the fluxes are falling small, but your perturbation theory breaks down there. If you go to 13,000 of the invariant mass, your perturbation theory breaks down. And this is only if I consider the threshold limit. What happens if I do not consider the threshold limit? If I consider the PT, instead of saying that my final state mass is carrying a certain energy, if my final state kinematical quantity is carrying a certain energy, say transverse momentum. So then there is also a similar problem will be there. If your observer carries a very large transverse momentum energy, then also you have the large PT logarithms, they will blow up and they follow the perturbation theory. And in the large PT region, you need to do the resummation of that kind of logarithms. Then you will not see the curly D type of logarithms, rather you will see a different type of logarithms. But the idea is the same. And the PT concept is a little tricky, so you can have a problem even the PT goes to 0 limit also. But we will not go into the present context, we will just confine to the threshold limit, threshold resummation. So with this, I think I'm just, so tomorrow what we do is I think, you can do a small exercise for yourself simply because it's school. You take a simple function, okay, so and then you can do this kind of integral, and this is what we call as the Milling transformation. Okay, for example, we have discussed the curly delay. Or you can take any simple regular polynomial function like AZ plus BZ squared plus CZ. Some this kind of simple polynomial function you take, and you just do this kind of integral, and this is called the Mellin integral. So you can convince yourself what comes on the as a result of this integral. Particularly if I take this logarithmic on the right hand side, and you see what you get on the left hand side. This is very, very important. You can also try to other type of functions, just taking simply log of 1 minus z, taking 1 minus z times log of 1 minus z. Okay? So what we do is I think here if you see this, the fluxes, whatever I have plotted here, the definition of the flux is this thing. Basically, you are taking integral of order distribution functions with some kinematic constraint. So that kinematic constraint is inherently this condition how we call x1, x2, where x1 and x2 are the integration variables, is what we call as a convolution. This is a classical example of convolution. Okay, and when you want to do the curlities also under this convolution, things become very complicated. And when you want to do higher and higher orders of convolutions, things become even more complicated. But it is not impossible to do. You can do it. And that is the case where if you go to the Mellin transformation, things become much easier actually. So we can have what we call as the Mellin moments. Okay. So no matter what we do is I think we just try to learn how to do the resummation in the Mellin space, and maybe we discuss few concepts of the factorization theorem and Mellin inversion. Maybe the time permits, or we discuss few universal applications. Okay. So that is all for the first few days session. So I will continue again tomorrow. Tomorrow my session is at 9:30, right?
Yes, in the morning. In the morning.
In the morning at 9:30, right?
Yes, yes.
Okay, fine.
So you can. Any question? Any question from the audience? Sir, you can stop sharing.
Okay, thank you, thank you.
Sir, Ravi is here.
Oh, okay. I forgot, it's a long time Okay, stop. I use Zoom after a long time.
Go to Zoom app. Zoom app.
Yeah, the Zoom app. This is a Zoom app. I'll just stop sharing.
No, in the above, in the violet, in the right, you can.
Somewhere this Zoom icon is there, sir. This or blue color. You click on that.
Blue color.
Upper. Above AMPS.
Do you see my screen first of all?
Yes, yes. Stop sharing.
Just reset the Dropbox.
I'll stop sharing. Yes, yes.
Okay. Okay.
Sir, you can talk.
Sorry, due to some unavoidable reasons, I could not come to this meeting. Otherwise, I believe this was such a energetic meeting. The way it happened in Mohali last time, I miss all that boost.
So, because you did not come, maybe you can organize the next meeting.
The punishment.
We all can come actually.
Yeah.
So we'll make you happy. It will not be punishment.
Yeah, sure. I will try, Ravi.
Because this is full. Next one will be, I think, workshop kind of thing. Like we had a workshop in Mohali, we call for a few months back. Like that. What do you think?
So, who are present in the meeting actually?
Which meeting?
I mean, in the present meeting, who are all present?
You can see already.
Okay, some tab is changed. Okay. Okay, good to see you all. Okay. So then we'll meet tomorrow in the morning at 9:30.
Satyajit left just now. But
Oh, okay,
half an hour
Satyajit
back.
left. Okay, fine. Yeah. So, did Anurag come today?
Today morning he was here, afternoon he left.
Oh, Anurag also left. Fine. So, okay, Ravi, okay, all right.
Sir, I have one doubt.
Yes, please.
So we can have distribution in Z also, right? Instead of 1 minus Z, we can have distribution in Z. Is that like
You have a problem when the Z goes to 0 limit, not in the Z goes to 1 limit.
But we can also have both. Is it possible or?
Yeah, you can have, but Z equal to 0 corresponds to your Q square by S goes to 0 limit. No, where Q square has to be very, very small. For example, if there is a classic question that you can ask in the dielectron invariant mass distribution. If you go to the very small Q value, actually, you can have the similar problem, but there you have the log Q square by S type of terms actually. So there you cannot, experimentally it may not be relevant because we always keep some cuts on the electrons itself. You need minimum 25 GeV cut. So you'll never go to that limit actually. But the similar problem exactly triggers when it comes to the PT distribution. Instead of the invariant mass, you go to the small PT, then this problem will come. And you have to deal with again the resummation concept. And there is no way there.
Thanks. Okay then,
Oh.
sir.
Okay then. Thank you all. See you tomorrow. Yes.
Okay.
टिकट लगेगा तुम्हारा टिकट है तो सब टिकट लगेगा उसके बाद ही मिलेगा नहीं उनका 16 अलग बात है तुमने यहाँ से आ जाना है वापिस भी आना बोर्डिंग पास भी लगेगा बोर्डिंग पास टिकट तो है ना टिकट दे दो उसके पास बोर्डिंग पास है वो बोर्डिंग चेक इन करके दे दे अरे आजकल फिर तुम्हें पूछा है क्या बात आप जा रहे हैं तो दे दो अभी मांगा तुमने कब तक वो हमें जाने से पहले देना तुम लोग सबमिट करोगे हम ही सबमिट करेंगे भाई तो जान लो नहीं भाई होगा चेन्नई टू बैंगलोर बैंगलोर टू चेन्नई ओके भाई
डिस्कशन अब जो आज
Next is discussion. Here we don't need anything like we don't need online anything. Discussion. There is nothing online and tomorrow what about? Ma'am, there will be tomorrow two sessions. One no online one session. One lecture. Research is also there, right? That is recording. It's okay for to be coming on Saturday.
Yeah, we'll come. Saturday you have.